lecture. I'm gonna now share the screen for Gloria. And Gloria, we can't wait to hear you. Yeah, please go on, Gloria. Thanks for making the presentation.
The radioactive decay and its application in cancer
therapy, that's right.
Therapy.
Do you want to change the slide?
Yes.
Okay.
The process by which an unstable nucleus spontaneously emits reaction and transform into another nucleus.
Oh, that's a very cool picture. Look at that. On the left, you have a radioactive nucleus. It means that the nucleus, which is unstable because we have different number of the protons and different number of, I should say, neutrons, that's why it's unstable. And it disintegrates. Huh? I borrowed that word from Philip. I didn't know that myself. We can use disintegration. Then we have new nucleus and also one helium atom. 2 protons, 2 neutrons. It represents the helium atom. And we have another new nucleus. And as you will see, the atomic number is changed from 92 to 90 because we had lost 2 protons because of the disintegration of the alpha particle, which is the helium atom. And also, you can see that here. The red represents the proton and the blue represents the neutron. And that's what happens after the radioactive disintegration. It gives rise to a new particle with a different atomic number from the beginning one, and also the alpha particle, which is essentially the helium atom. Plus, we have also, look at this on the right. Oh my God, Gloria, thanks for this picture. That's a beautiful picture. We can talk about that a lot. You see that the same pictures on the right, you see that it gives us also to the beta decay, which you see the electrons with the negative signs, they are getting with the high speed going out. They call that beta radiation. And also we have gamma radiation in terms of the photon, that I also borrowed that word from Philip, that you see that it radiates with a very high energy outside. But these pictures, Gloria, fantastic job. I love these pictures which you selected because not only the colors is so beautiful, but also it has lots of knowledge behind it. Thanks. Okay. Look at that, this one also, we have a neutron which disintegrates into a proton, an electron, and the radiation. You see that? That's the radiation that we talked. That's a very advanced thing in the quantum physics. The neutron disintegrates into proton, electron, and the radiation. Thanks. Give me 1 second. I'm just going to write it myself, Gloria.
Okay.
I'm going to learn that later. I'm going to do a search myself. Neutron goes to proton, goes to electron, and goes to radiation. Awesome. Thanks. Should I change the slide or no, you have something else?
Change the slide. In the vast majority of nucleus, they are unstable. Yes, the next one.
Okay, let me see. And I have something more. They will spontaneously sharp change into another nuclei and emit all kinds of rays at the same time. Radioactive decay, that's right. That's what we talked on the previous slide, huh?
Yes.
Very nice. Oh my God. This picture looks very familiar. This one is good also. Good slides. Thanks, Gloria.
Including the decay of alpha, beta, and Y.
Oh my God, look at this picture. I think that's an organic compound, huh?
Mm,
Alpha, beta, what is that? Gamma factorization, metal-free mild condition. I think it's a little bit different. I think the alpha decay, it represents the alpha carbon, which is gonna be different from your presentation from the alpha decay or beta decay, because these ones represent something in chemistry which calls the alpha carbon or the beta carbon, I think, and that's these organic compounds. But I think they are not exactly related to the radioactive decay, or maybe I'm not sure, but it mostly I think they refer to a chemical reaction and the alpha or beta carbon of a compound, which I do suspect. But that's good that you presented these ones because they are very cool looking molecular compounds in organic chemistry. Thanks, Gloria. Next slide.
yes.
Yeah.
The history of radiation nuclear supply can be traced back to the early 1900s after the discovery of radioactivity by Harry Curie and Marie Curie. And this is the story.
Let us read. Becquerel. Some severe inflammation of his skin. Oh, let me read that. You don't mind if I read it, Gloria?
Yes.
In 1901, Becquerel experienced some severe inflammation of his skin. Oh, it means that something happened into his skin. It was inflamed of his skin after placing a tube of radium in his waistcoat pocket for several hours. Oh, it was a radium material, which is a radioactive one, because radium, as you will see, it is a radioactive material. His discovery led to the first use of radium in therapy when Henry Alexander Downlows, an organ block, placed radium in contact with the tuberculosis. Oh my God, what is that word? So hard to pronounce. Tuberculous skin lesion. In 1903, Alexander Graham Bell suggested placing sources containing radium, which is a radioactive material, in or near tumors. Oh my God, it's very interesting that Alexander Graham Bell, which I remember him as an inventor of the phone. Am I right, guys?
Yes.
Inventor of the phone. He suggested actually to place a radioactive material, the radium, near a tumor. And in 1913, Frederick Proscher published the first study on the intravenous injection. Guys, intravenous injection means what? Intravein means the thing which the blood flows inside your body. Intravenous injection means that they inject the radioactive material inside your body. And it seems that it was suggested in 1930 by the Frederick Proscher that you can inject radium for therapy of various type of diseases. Oh my God, that's so interesting. I didn't know that Alexander Graham Bell was the first person who suggested putting radium inside or near a cancerous tumors, in order to kill it. Interesting, interesting. Thanks for putting that slide there. Next slide.
Yes. In the last 20 years, in the clear supply has been widely used in various clinical, management, and plant management applications.
Uh-huh. Okay. Do you want me to read that, the rest?
Yes.
These slides is very good. They have lots of good information. In the last 20 years, radionuclide therapy has been widely used in various clinical, malignant, and pain management applications. Guys, look at that. Malignant means clinical, means that when you go to a hospital, clinical. Malignant means the type of the cancer that it may kill someone. It's not benign. It's very, malignant means malignant, dangerous, very dangerous. Radionuclides such as iodine 131, phosphorus 32, strontium 90, and yttrium. Oh my God, such a cool names. It's the first time I see them. Yttrium 90 have been successfully used in the treatment of the benign and malignant diseases, phosphorus, iodine, with the application of the new radionuclides and drugs in the treatment of the pain of bone metastasis. Metastasis means that when the cancer proliferates so fastly. Neurodendrocrine. Oh my God, let me write that word. I never saw that. I'm going to research it. Neuro means coming from the neurons, the brain. Neuroendocrine tumors and other benign and malignant tumors. Benign means a type of the tumors, the cancer cells, which they are okay. They are not very dangerous. They may not kill someone. But malignant means the tumor which is very dangerous. Radionuclide therapy has developed rapidly. Currently, radionuclide therapy has entered a vigorous development stage in Asia. The high incidence rate of the thyroid and liver tumors has promoted the development of the radionuclide therapy and targeted therapy. Very interesting. Radio, these two words, it's so interesting. Radionuclide. Therapy and also neuroendocrine tumors. It's these two words, I love them. It's so hard to pronounce them, but they are so interesting words. Awesome. Thanks, Gloria, for lots of knowledge you put in these slides. Okay.
We need to evaluate where every radionuclide or radio-pharmaceutical for its suitability for clinical usage.
Right. That word is very hard. I think let me try to see if I can read it. Radio-pharmaceutical. Radio-pharmaceutical means when it comes to the pharmaceutical research, when they develop the drugs to cure diseases. Radio-pharmaceutical. Oh my God. Gloria.
Yes.
I have one thing to ask you.
Yes.
Today I learned, I'm writing these ones, I learned so many new words from your presentation. Radio-pharmaceutical, I'm writing them to learn them before. You have 3 slides. They are the definitions, huh?
Yes.
Let me see. Radio-pharmaceuticals are attached to the radionuclide in order to send it to the desired target within the body. Guys, I'm reading these slides from left to the right, and I have to say there are lots of knowledge in there. Pharmaceuticals are labels are attached to the radionuclides in order to send it to the desired target within the body. The resultant mixture is called radio-pharmaceuticals. That's right. The radio-pharmaceuticals with the radionuclide becomes radio-pharmaceuticals. They compose of a radionuclide bound to organic molecules. Radiopharmaceuticals are designed to concentrate on a particular organ. They mimic a natural physiologic process. They evaluate functions rather than an anatomy. let me see the next one. The radioactive materials administered to patients are known as radiopharmaceuticals. They consist of chemical molecules, which determines the behavior of the radiopharmaceuticals in the body, and the radionucleotide, that the radiation emitted by the radionucleotide may be detected from outside of the body in a radionucleotide imaging device, such as gamma camera, or may be detected in a sample of the body fluid, such as plasma or urine. Oh my God, this is phenomenal. I never knew this before. Radiopharmaceuticals, chemical. Okay, radionucleotide. Okay, and the last one, last slide, that's the radionucleotide. The radioactive components of radiopharmaceuticals is referred to as a radionuclide. The nuclides are identified as atoms having a specific number of the protons and the neutrons in the nucleus. A nuclide is typically identified by chemical symbols to the elements within a mass number, which the mass number equals to the sum of the number of the neutrons and the number of the protons in the nuclides. I think that's about more the chemistry shown as a superscripts indicating the sum of the protons and neutrons. Interesting. When the atom is radioactive, it is called radionuclide. Interesting. Oh my God, this one single slide has hundreds of things to learn. Oh my God, thanks Gloria for, but I think guys, the important thing is that this slide represents that, for example, in pharmacy, radiopharmaceutical is that they attach the radioactive decay materials, which they call that radionuclide, into, I should say, pharmaceuticals to take the radioactive material into the organ of the interest. Interesting, interesting. Thanks, Gloria. Next slide.
Yes.
Okay.
The most important factor to be considered when choosing a suitable radionuclide for therapy is the effective half-life, which is the net half-life considering both physical half-life and biological half-life within the patient's body or organism.
Okay, do you want me to continue?
Yes.
Thanks. Okay, you said that the determination of effective half-life, which you called it T, subindex E, which T stands for time, E stands for effective. Am I right, Gloria?
Yes.
Is explained in the medical internal radiation, oh my God, dosimetry, which it means that the dose, the amount of radiation which they can just tolerate, calculation method, which is summarized as the effective time equals to TP multiplied to each other divided by TP plus TB. But what is TB is the biological half-life and TP is the physical half-life. Am I right?
Yes.
The physical half-life, which is the TP, is readily available from the published radionuclide data. But the biological half-life requires knowledge of the radio tracers, spatial and temporal distribution within the body. Oh my God, that's very advanced. This includes radio tracers delivery, uptake, which it means that it takes, metabolism, clearance, and excretion within the patient's body. Therefore, for an effective radiation therapy, effective radiation delivery, a balanced, optimal, biological, and physical half-life should be chosen. which results in optimal effective half-life. That is very interesting and so hard. This page is lots of information. Effective time, which is the effective biological determination of the effective half-life. Effective half-life, then that's the product of two half-life, biological and physical, which is very interesting, Physical, biological. And also you said that the biological half-life requires a kind of a distribution, spatial and temporal. We have to know radio tracer delivery, uptake, metabolism, clearance. Oh my God, lots of stuff. Interesting. Thanks. Should I go to the next slide?
Yes.
Let me go to the next one.
Okay. Various radionuclides have been discovered or developed for therapeutic process since the first use of radium in the early 1900s.
You want me to continue?
And this is the information for this.
That's right. You don't mind if I continue the rest?
Yes.
Yeah, it says that the most commonly used therapeutic radionuclide today is iodine or iodine, which is the radioactive from the iode material 131 labeled with sodium iodine in capsule or liquid form. The treatment is widely known as a radioactive iodine therapy. Let me write that, Gloria, for myself.
Okay.
Because I need to just teach myself radioactive iodine therapy, which uses iodine 131 to treat thyroid-related disease. Another major applications of the radionuclide therapy is in the treatment of the bone metastasis, which is a kind of a thing that the cancer grows so fast. The radiopharmaceutical travels selectively to the volumes of the damaged bones. The radiopharmaceuticals travel selectively to the volumes of the damaged bones while sparing normal undamaged bones. Most of the radionuclides used are beta emitters. Beta emitters, which one is the, Gloria? Is the electrons, which they emit from the nucleotides,
Yes.
Awesome. Should I go to the next page?
Yes. And there is a table on the next slide.
Okay, should I go next one?
Yes.
And your table summarizes the most commonly used radiopharmaceuticals for targeted radionuclide therapy. Okay, it's very interesting. I can't wait to see that. Let's go to the, oh my God, look at this one. You have, for example, radiopharmaceuticals. This is iodine. Oh my God, chloride, calcium analog, targeted mechanism, indication. It's for liver. Oh, we have different type of cancers. For example, iodine is for thyroid cancer. We have chloride, for example, for the bone pain palliation, bone neuroendocrine tumors, which is why I cannot even pronounce them. So hard. I love the last one, which is IMIBG, active transport into the neuroendocrine cells, which is for the neuroblastoma, oh my God, carcinoid. Oh my God, I cannot pronounce them, man. It's so hard. But I know that they're connected to the brain type of tumors there. Oh my God, thanks for including that chart there, Gloria. Thank you. Fantastic. But it's so hard to pronounce them. So hard. Okay, should I go to the next slide?
Yes.
Imagine, for example, this one. Chroma. Oh my God, I cannot. I go to the next slide. Don't mind. So hard. Okay. I'm trying to go to the next. Okay.
Therapeutic nuclear medicate is developing rapidly as an alternative choice of treatment in oncology.
That's right. Oncology, guys, the thing which I want you all, please look into this, is the concepts of the oncology. Because if you're interested with the math, you can go to the medical school, then you can just do a research on how to treat the cancers. And there are lots of applications these now that you use mathematical modeling in order to make a prediction of how the drugs which they can be designed to do a targeted medicine. And it requires a good knowledge of the math and computer science. You don't mind if I continue with that, with the reading on Gloria?
Yes.
Thanks. Other than its traditional uses in endocrinology and rheumatology, therapeutic radionuclides have now gained attention for tumor targeting therapy using multiple routes and mechanisms to target radionuclides in the tumor sites. The non-invasiveness of the procedure and the relatively non-invasiveness, it means that you do not need to use the surgery, because sometimes in order to treat the cancer, you do have to just do a surgery, and the surgeon cuts the part of the brain and extracts and remove the tumor cells from that tissue. But the non-invasiveness, it means that you do not need to use the surgery. The non-invasiveness of the procedure and relatively low toxicity, it means that it's not toxic, it's not producing the poison. In comparison to conventional chemotherapy and external beam radiotherapy, makes radionuclide therapy an attractive and realistic alternative in the management of the benign and malignant diseases. Oh my God, I love that. I'm so excited to read this one. Look how important is that. I read that once more. The non-invasiveness means that you do not need the surgery of the procedure and relatively low toxicity. Toxicity means not poisonous in comparisons to the conventional chemotherapy and external beam radiotherapy, makes radionuclide therapy an attractive and realistic alternative in the management of benign and malignant diseases. Fantastic. I'm so excited for this presentation. Next slide.
I'm
Oh my
finished.
God. Gloria. It was brilliant. Thank you very much. Thanks.
Thank you.
Thank you. I should say it was like the university level presentation. You had lots of high level information in your presentation, which it was great. And I wrote some new stuff myself in order to do some research myself when the class is over, to educate myself about, for example, neuroendocrine or radiopharmaceuticals. These stuff was so interesting. Thank you very much, Gloria. It was a wonderful presentation, and I appreciate the work which you did and the time that you put into preparing these materials. Thank you. Okay, let me stop.